previously we introduced the individual particle partition function, Q, right? And so when we introduced Q, basically we used it in such a way that it normalized our probability distribution for identifying what energy level a particle is in. But in general, the partition function, little q, basically the way to think about it is it just tells you the total number of available energy states that a particle can access. All right? And so, because q is, involved with the probability distribution, and it basically is just a summation of something that's proportional to the probability distribution, the partition function is going to have a lot of the same mathematical properties as the probability distribution has. So partition functions have same mathematical properties as probabilities. Okay? And so we're going to take advantage of that fact in a bit. But the lowercase q that we defined here, that was the partition function for like an individual particle. If we're dealing with a system made up of n particles, system of n independent particles, what we could do is we could also define the total system partition function. Define total system partition function. And we're going to call that capital Q. And just to emphasize, this is different than heat, not to be confused with heat. Okay? Now for the total system partition function, it's going to be related to the individual particle partition function, but the relationship is going to depend on whether the particles are indistinguishable or distinguishable from one another. And so for the distinguishable case, where particle 1 is different from particle 2, which is different from particle 3, Q, capital Q, is really just going to be the multiplicative product of the partition functions for each of the individual particles. So Q1 times Q2 times Q3 dot 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 times Qn, right? And because, each of these particles could access the same sort of energy levels, all of their individual particle functions are the same, right? So really what we end up with is Q raised to the n power. All right? So that's what the total partition function is for the distinguishable case. For the indistinguishable case, where particle 1 is the same as particle 2, and so on and so forth, to avoid overcounting, what we do is we just take our q raised to the n, and we have to divide it by the factorial of the number of particles that we have. Okay? All right, so those, you could define a total system partition function as well. But the reason why I'm introducing the individual and the total system partition function now is because it turns out we could actually relate them directly to various thermodynamic properties. Okay? All right, and so to show an example of this, let's go through the act of calculating U and S, so internal energy and entropy, for a system in which we have the temperature, volume, and number of molecules fixed. Okay? And in this system, we're going to consider that the particles are indistinguishable from one another. So indistinguishable particles. And essentially, what we're describing is just a gas, right? So in a gas, all the different molecules, for if you just have one chemical, all these molecules are basically going to be the same as one another. You can't distinguish between them. Okay? All right, so we're going to calculate U and S for this type of system. And we're going to do it first if we're just dealing with an individual particle, such that the lowercase q partition function is what's going to be important here. All right, so the internal energy, as we derived previously, we could relate that to the probability via this sort of equation, where this epsilon here, that's just the energy energy of the ith level in our system. Okay. For the probability, we could rewrite that in terms of the partition function. So we'll move epsilon over here, and then we could write the probability like this. Okay? Where, just once again, lowercase q is just a summation of our Boltzmann factors. Okay? All right. So here we have q, and really we have the summation of q. So we already take the summation in here. And so that means that q is basically just like a constant, right? That's it's just going to be a static value. And so because it's a static value, we could take it outside of the summation. So q can go here, and in the summation, we have this left. Okay? All right, and what I'm going to do, and what's commonly seen in the literature, is this kBt term, or 1 over kBt, I'm going to define as this variable beta. Right? And so I'm doing that because it's, kind of makes the equation a little bit easier to write, and we'll take advantage of that fact in a little bit. In any case, so the internal energy, it's going to be 1 over q times the summation of epsilon I exponential negative beta epsilon I. Right, so we have this nice compact form. All right, what I want to do now, we have this q. What I want to do is I want to take the partial derivative of q with respect to beta. So we have d beta, and here's our equation for q. So summation of I t exponential epsilon kb, I'm going to write this in terms of beta. Okay? All right, and so, parentheses here, when we take that derivative, we get this. I exponential beta epsilon I. All right? In fact, just to bring home my next point more clearly, and make this a square bracket. All right? And so as you could tell, when we take the derivative of q with respect to beta, we get this term, right? And this term is the same exact thing as that term. And so that means that what we could do is we could rewrite the internal energy using this partial derivative. So I'm going to go to the next page. So we have u, and that's going to be equal to negative 1 over q dq d beta. Right? So I'm just taking the partial derivative from the previous page. So we have 1 over q times the derivative of q with respect to beta. As you know, in this form, this is the same thing as just taking the derivative of the natural log of q. Okay? What I'm going to do now is we have to remember that beta here, this is just 1 over kBt. Right? And so what I'm going to do, I'm just going to kind of play a trick here, is I'm going to employ the chain rule so that I could rewrite this partial derivative like this. dln of q dt times dt d beta. Right? And so all I did was employ the chain rule. And what we have now, because we know that beta and t are related to one another, we could actually take this sort of derivative, and when we do that, what it's going to give us is negative kb t squared. Okay? So our internal energy, we could actually rewrite as kt squared d ln of q dt. Okay? All right, so we have an expression for the internal energy for the individual particle, right? And so if we have knowledge of what our partition function is, then we could calculate the internal energy of the system just by using this expression. All right, so this was for the individual particle. What we could do now is we could calculate the internal energy for the total system. Okay? So for the total system, in the end, we could go through a similar sort of derivation, and we'll get something that looks like this, except this time, we're going to use the total system partition function. dt. All right? And what I'll do now is we know that the total system partition function for a system with indistinguishable particles is just this. Okay? So we'll go out and write that derivative. So I'll factor out the kt squared. And since we have two things here, we have to apply the quotient rule. So we're going to get d ln of qn divided by n naught there. Oh, whoops. Not that. And so in the end, when we take that first derivative, since we have ln of, well, when we take that first derivative, the n factorial will cancel. So we're just left with that. And here, for this second term, we have d ln n factorial dt. Okay. Here, n factorial, that's just the number of particles, and that's independent of temperature. So that's going to be 0. All right, in here, we could play around with our natural log rules, and since we have n as an exponent, we could bring that down. And so we find that our internal energy is then just going to be nkb t squared d ln of q dt. All right? So this is what the internal energy would be for the total system. Okay? The last thing I'm going to do, we calculated the internal energy. Let's now calculate the entropy of the system. So we're going to calculate entropy for fixed TVN system with indistinguishable particles. Okay? Alright, so previously we showed that the entropy can be written as a function of probabilities like this. Okay? Alright, and so we could rewrite the probabilities in terms, since we're dealing with the total system, we could write it in terms of the total system partition function, and it will look like this. So we just plug in the probabilities. So we have 1 over q times the exponential of negative epsilon kbt, and then we'll take the natural log of 1 over q, and then taking the natural log of an exponential, this just comes out. Okay. All right. What I'll do now is I'll distribute across this term. All right. And so when I distribute that across, we'll get the following. Okay. So here, since we have 1 over q in the natural log, I'll just factor out the negative. So I'll play around with the log rules again. So I'll get kb ln of q over q, and then times this summation. All right. All right, and so all I did was just distribute across the kb and this to the other two terms. Okay? All right, so after distributing that across, we know, since we have this, right? We know that by definition that this is just equal, I'll write it up here. We have the summation of the Boltzmann terms, and so we know by definition that this is just going to be our q. Okay? All right, so if we have q there and q here, then this q is going to cancel. Okay? The other thing I want to point out is here we have epsilon I over big Q, and then the exponential term. This, as we showed before, is just our internal energy, or one way to express our internal energy. Okay? All right, and so plugging those things in, what we get is that the entropy is just going to be equal to kb ln of big Q plus internal energy divided by temperature. And since the big Q is just equal to this, what we get is nkb ln of little q plus u divided by t. We're once again playing around with the log rules. I just brought down the n here.